Hey guys, Mr. Riz to help you guys out again. Once again, I have individual videos here of all the 312 to 314 lessons. This one here, we're looking at or 315 lessons. This one is 314. So we're looking at CO2 here. And let's go ahead and jump into it, kind of see what's going on. Once again, I'm not going to answer all the questions for you, but I should be able to help you guys out here, figure some things out, clarify some questions, making sure you guys get some help with this lab here. So with this, we want to make sure that we have our CO2 detector and our software. We are going to we're going to need some water here. I'm not going to do that experiment with you guys, but I'll kind of talk about what you'll do. And then we'll need to have some water, some yeast, some sugar, some measuring cups, and then this data sample sheet here. So I'm going to go ahead, open it up in a new tab. So this is a sample sheet that I've started. You are going to add to this sample sheet. So you will make a copy of this. Yep. And that way you have some information and then we can collect more. So now you have something that you can go through and add onto it. And that's what I'm going to be looking for in the experiment. So first thing we want to do is kind of understand CO2, how it's used. So the CO2 sensor will measure the carbon dioxide in the air. First thing we're going to do is see how much carbon dioxide we can produce in a single breath. And we're going to use the CO2 to kind of help use that or analyze that to figure out, okay, the rapid yeast production of CO2. Or yeah, the rapid yeast production of CO2. So ultimate goal is to figure out what's the best ratio to produce the most CO2 or produce CO2 the fastest. All right, so we're going to connect the sensor here to Vernier. And if you already have it connected and then you open up the software, that seems to be the best format here. We will need to kind of double check our collection settings here. So this should open up. And I say that, and it's not. I'm going to pause it. Well, let me try it again. Let's go to Vernier, graphical analysis. It's connected. Okay, there we go. So let's go down here to the sensor, make sure our sensor channels are on. We want to do CO2 gas, not temperature, although I'd love to see the temperature in this room right now. Side note, I do have the space heater running in this room here because it's very, very cold. And then over here, we're going to change the rate here. We're going to have a rate of 2 collections. So that's an interval of 0.5. We're going to manually trigger the start and manually trigger the end collection. All right, and everything we're going to be doing is time-based. Okay, so the first thing we're going to do is click collect, and then we're going to breathe into the sensor for 60 seconds and watch what happens. Now, for the sake of this video, I won't go for 60 seconds, but this is like some ASMR stuff, right? Okay, you can see. Okay, that's long enough that you guys need to watch a video of me breathing into this. So we can let each person in this group to kind of see if there's any difference. But when we do that, we're going to go to this left and we can, hide all data sets if we want to go through individual ones. So the first question, what is the average CO2 per parts per million? So what we want to do is figure out the average. I can let you guys kind of decide what that is. So you can argue that the average is right here where it kind of plateaus. You can say the average is here in the middle. You definitely wouldn't want to go down here. Now, technically, the average would be if we could take the integral and go through here, which I'm wondering now, they've done some things here. View integral. Can we do that? So, oh, that's weird. Okay. Integral 0 to 20 area. That does not help me out. Okay, actually, they're 7 point. Okay, that's not helping me out. I guess if we did the math, prediction, add manual fit, view statistics. Oh, okay, here we go. There's the mean. So the mean, the average, 3710 parts per million. That's going to write down. All right. So what's the average estimate? Oh, okay. So my bad. We were supposed to do that just in the room as it is first. So we just run the test as is, going through this, let it go for 60 seconds. collect, look at that statistics, and then do it where we are breathing. Nope, cancel. I didn't want to close it out. I want to minimize it. Make sure we read the directions, Mr. Riz. All right, so next thing we're going to do is we're going to run a real long experiment. And this is definitely one of those tests where you guys can start this here, you'd run it, and while it's running on your friend's partner's computer, you do a different lab. So what we're going to do is we are going to have the yeast produce CO2 in an experiment, but what we're going to do is have 30 milliliters of water in there. You're going to put up to 2 teaspoons of yeast and up to 2 teaspoons of sugar. Now, if we look at the sample data here, there are some that have already been done. So here's 1 teaspoon of yeast and a half teaspoon of sugar. Here's 2 of both. Here's 2 teaspoons of yeast and 1 of sugar, 2 teaspoons and a half of sugar, half teaspoon. So try to find a combination that isn't on here, like 1 teaspoon of yeast and 1 teaspoon of sugar, or a half teaspoon of yeast. Oh, no, we already got that one. How about 1 teaspoon of yeast and 2 teaspoons of sugar? Okay, that has been on there, or 1.5. Some combination that isn't on here that you are going to then write here on the test. All right, so you decide the amounts, you'll add that to your table, and then what you're going to do is put all the liquids in there. You shake it up, and you can see from this picture here, you're going to put the CO2 detector in there, and you're going to press collect. And so you'll just let it collect, and you will see it will build up. Now, after it gets done, you're going to look at the data table here, and you're going to copy some of that over. So let's imagine I did this first one here. I would select this data table. I'm just doing Control C on my keyboard to copy it. I'd go to this over here and then paste it down. Now, technically, I only needed this column here. I don't need the seconds because they're already there. I can delete that and look at that here. So I would say like this is, actually this is Mr. Riz breathing. Riz breathing. You don't want to use your breathing. You want to do breathe, whatever. It's just Riz. You want to use the yeast information that you get. Okay. So next, okay, we got that. We have our own copy. We edit that chart. We can go through and set it up as a line chart. So what we want to do here is that for each one of these, or what you can kind of do here, we select these all, get rid of this delete column. If we select these, we should be able to do insert chart, and we can do like a line chart. You might want to do a smooth line chart. Okay, now we don't need to have the time on here because that should actually be our x-axis is the time. We can remove the time, and then we can see everything else. Now, some of these tests are way longer. Okay, like this one test here that has 1 teaspoon of yeast and the rest is way longer than the other ones on here. You can see this one here even like maxed out the counter. Okay, but hopefully when you add yours onto this table, you can see it. Yeah, Mr. Riz isn't even shown on here. We can do some other things with this table too. If we're not seeing enough, we can increase the size of it. We can go through some of the table graph options here and change like the axes, the labels. We can change the min and max values of those axes. So the horizontal, maybe we only want to go to, I'll do 2000. Wait, I did 200 there. I said 2000, but I typed in 200. Okay. Yeah, minimum value would be 0. So we can kind of see a little bit better there. Now, actually, maybe go 5,000. That'd be a little bit better. Okay. That's probably better. You can even see so this is 5,000 seconds. That's a really long time. And we can see what's going on here afterwards. I don't know why I'm not able to move that around. It's probably just my window settings here. So we're going to go through, set that up as a table, and be good from there. So next, we're going to place your cursor on the lines. At what cell did the 2 teaspoons yeast and 2 teaspoons sugar stop changing? So, man, I wish I could move this out of the way. I'm going to just delete this table for the sake purpose. And did that freeze? Can I delete? All right, so we're only looking at teaspoon, 2 teaspoons yeast. We're going to figure out when did this stop growing. Now, if we wanted to, probably could just look at this as a visual. So we'll do insert chart. And it appears it stopped. Column chart, we'll do smooth line one right here. Fortunately, I can't click on this, but it looks to be 10,000. So we have to scroll, 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 and we should be able to find. Oh man, wish I could go through this faster. Oh yeah, I could use this bar here. 20. Oh, these are okay. There we go. 10,000, 10,000. Stops right there. And that looks at to be about 39.78. Okay. So if we look here, looking at the trend, both of the slope and lines, what might you assume around that 4,000 mark? So around 4,000, this is what's going on. What is going on here with this graphic? Are we just reaching at 100,000 parts per million? No. What's probably going is we're exceeding that value, and our thermometer just can't read anything above 100,000. Kind of like one of those experiments that we did before where we looked to see, why is this graph not working or what happened with the experiment. All right, so what we can do now here is we can then delete all the data after this row and to make our lives easier. So to do this, what we can do if we want to select a large group, we can click on that and use the shift key. And then we can click down to the bottom here. So I got that. I'm going to scroll down to the bottom here. Click down here at the bottom, and it's going to select everything, and then we just click delete. Okay. More information than we needed to. We might also want to go through and do that for the other series. So there's an easy way that we can do that. We can customize the tabs and apply to all. So I would recommend you guys trying that. But for the sake of purposes here, I'm going to go through, do that again here. So where is that? 4,000, I think was the mark here. Boom, boom. Scroll all the way down to the bottom. I clicked, I felt, okay, cool. There we go. That was quick. And then we're going to see if there is the trend line. So we can go back here now, look at our graphs. This should be neater. Delete that graph. So if we want to go back and look at everything, insert. Now, if we already have our chart here, it's just going to be modifying. And yep, let's do smooth line chart here. And we can see now this graph is a lot easier. We can see some of the first tests that were cut short, and we can see the really short RIS test, but we can see the other ones as well. I mean, hopefully you see your test that you made going through. If we needed to change any of those things, we can change the thickness on it to go through. So next, when does the trend point? Okay, so what we need to do here is actually get the trend line. So that's what I was skipping out on. So in the chart editor, you know what I'm going to do? Split screen this here so we can see both of those. Boom, boom. We are in the chart editor. We need to click the customize, move my head here, customize. And we are going to expand the series. And then with that, we're going to go to apply to all series. We're going to select the 1 tablespoon for half teaspoons part per million. And then what we're going to do here, click the checkbox for trend line. And then we're going to go select linear, which it is. And we can have our trend line color. I'm going to pick something that really stands out here. Maybe it's purple. And then we can change the thickness here to make it even more apparent of what's going on. So we can see the trend line of that graph. Okay, so this isn't the model, but this is like our y equals mx plus b of that. We could do that same thing here if we wanted to with this one. We could also set up a trend line. You can see that. We can make it thicker so we can see. Here is the trend line of the 2 tablespoons for 2 teaspoons. We can do that with all. So if we're looking at those 2 tablespoons to 2 teaspoons, what we want to do is we want to figure out when the line deviates from the trend. So we can actually look at this. So if you know anything about math here, we would say that the graph actually is exponential growth. We have this curved line that's going up. Now, our trend line is this diagonal line here of a linear graph of y equals mx plus b. And there's 2 points where it doesn't fit. There's one point here at the beginning where we actually have values that are switching from being above what we normally get in the trend. And that's just because the b number has to be so low. What we want to do here is to look kind of at this value. We should be able to, if we click on this graph here, let's see, or, even let's go to our horizontal axis. Actually, that's in our setup. Oh, we don't have an X. That's why we don't have a time. We can see here roughly at this data point. I don't know why it's not letting me select that data point right here. We can say that it's around the 3,500 mark where it stops fitting the trend line. You should be able, and you guys are probably doing it. I might be in a setup with my Zoom screen here that I can't actually click on that number here. Setup. No, I don't want to do aggregate. Maybe if I close that out, can I select? There we go. There we go. I can hover over the mouse. So yeah, I guess 3,500 or so it looks like around 3,400 seconds that it switches and actually is more than our trend line. Okay, so what kind of trend line might the data follow after it stops following that, after it? So the trend line is a linear. So after we start fitting the exponential, maybe we'd want to do something. And this is where we can double click on this. And we can look at the trend line and maybe do what's exponential. Okay, that's closer. Polynomial, it's a little off. Logarithmic, no, complete opposite. Power series, way off. Moving average, that is actually really close. So here's where you would go through and edit those changes and see, what the trend line actually would be closer to either exponential or moving average. Okay, so linear equation here is set up into y equals mx plus b. Exponential is in the form of x to the y power. So what do the 2 different lines suggest about the different growth rates of CO2 in this data? So if we look at the one, this is a fairly linear graph here, right? If we look back at the trend line, we're looking at a flat, and does it even show? Right here, we probably can show, oh, that's the R. But we can use the equation for the y equals mx plus b. I'm going to go back to this one here. I'm going to show label. Let's use the equation. All right, so the one we can see here is like y equals mx plus b. I got like 5.08x plus 4,000 over here. Oh man, that's a crazy number here. 15e to the x times, okay. That is insane. But what do the 2 different lines suggest about the different growth rates? So if we're looking at this 1 teaspoon for half tablespoon, it is linear. It is growing the same amount every second. It's growing about 5 parts per million per second. So 5 ppm per second. Now with the exponential, it's growing at a different rate per second. So the first time it's going slowly, and then it's going to double that value, and then double that value. So it starts out at 1 parts per million per second, 1 ppm per second. And then the next one is 2 ppm per second. And then it grows by 4 ppm per second, and then 8 ppm per second. So the growth is constantly doubling, or a value here that is represented. So it's exponential growth. Okay, so next thing we want to do is to think about our Google function list that we can use and try to figure out information about the data set. So we're going to look for all of these here, and we are going to predict, or not predict, but find the mean, the median, and the mode. So an easy way to do that, once again, I don't like the settings here. I'm going to just let's see if we can insert a column to the left of this. Sure. And I'm going to just type in mean, and you can equals mean. Oh, not mean. Mean is average. And we're going to say this is in column C2 to column C, what was it, 4,000? And there's the average. Okay. Then what we can do is find the slope. Okay. So equals slope. We can start with C2 with C 4,000. All right, yeah, that's not okay. So the mean, the slope of each data set. Oh, that was in the table. That was our mx plus b. Okay. Oh, that's the mean. We want to find mode. Mode, okay, is C2 colon C 4,000. All right, here's the most often one. And the standard deviation, ST dev, and then C2 colon C 4,000 is there. Now to get the slope, once again, I apologize, guys. You're going to go to insert. We'll do our chart. Looking back at our chart here, smooth line chart, I am going to go through and customize this by adding a trend line here. The trend line is going to be linear, and I'm going to just use that equation that's on here. So here is the slope is 5.08. So there is the slope of that one. All right, you guys are going to do that for each data set here. So let me insert a column to the left here. Now, we kind of know that this is average. Oh, you know what? Let me just Control X, Control V. I actually didn't mean to do that much. We had, what was after average? This was mode, Control X, Control V. And this is standard deviation. It's right here. Okay. And now if I do this right, I should be able to do Control C, Control V, and there we go. And that does for this column here. So here's the mean of this, here's the mode, and there's the standard deviation. I can insert a column to the left here and paste in those cells again, just double checking average, column G2. All right. And we can keep this going, insert column rows above. And then we also want to go through in each one of these, look at the slope of the line. So just make a table of this, select it. Oh, I'm drawing. Here we go. Insert. We'll do chart. Best thing to do is a smooth line chart. Just make sure we go to customize. We go to the series. Change the line color for this one. What? Oh, sure. And we want to go to a trend line, linear, and just make sure on our label we show the equation. So here is the actual data, and here's the slope here at 12.6. Okay, so you have each one of those listed out. Okay. Next, okay, so now we're going to think about the practicality of this. So the tiny holes in the bread are caused by the CO2 made by the yeast and the sugar. So the faster the CO2 production, the greater the CO2 amounts makes the fluffier bed. So what does the graph slope indicate about the bread's fluffiness? Once again, the faster growth means the fluffier bread. So what we wanted, the graph slope indicates how quickly it's going to be fluffier. All right. Does a lower or higher value make bread fluffier? The higher value should be fluffier. We are producing more parts per million. If the slope is higher, it's going to make fluffier bread. Okay, we're going to have higher parts per million. All right, next. The yeast consumed by the sugar, the yeast consumes the sugar and releases CO2. Over time, the container can fill up with more CO2. At what rate? At the rate at which it's filled up varied by the yeast and the sugar amount of the food. Similarity, will the earth ever fill up with CO2 from all the animals and things releasing CO2 in the air? So think about that. If we have a closed system here, eventually we're going to completely fill that thing up with CO2. Okay. Our atmosphere is technically a closed system right here. We're eating things, we're converting them to CO2. Will we ever just completely fill up our container of CO2? No, because there's things called plants, right? And they convert that CO2 back into oxygen. So if we had plants involved in this, probably we'll be getting a lot of different values. course, we probably would be producing more CO2 than the plants can handle, and then things can happen there too. All right. Would you consider the data that you collected here being access big or small data? So if you think about it, each one of these probably has over 4,000 data sets, and we're talking about 5 or 6 different data. So we're about 24,000 different. All right. We can say that's fairly large. We would not be able to do that by hand. In the grand scheme of things, though, this is still pretty small data. You think about a website collects millions of pieces of information from millions of people, hundreds of billions and trillions of information gone through all the time that needs to be sorted. How many websites are linked on Google? The search engine there too is just massive. So that is really big data in the grand scheme of things. This is fairly small. And what could be some limitations of expanding data beyond the tool that we collected? So just try to think about what we were able to do here and what's our limitation. We once saw our limitation with the tool that we use. It saw the highest values at 100,000. And after that, it just stopped. It was just maxing out of that. Some other limitation, just purely time. This experiment takes a long time to do. Your computer, your Chromebook might have gone off and turned off, making this experiment, null and void. Um, some other limitations too. Your temperature that you are at. You can have 2 different yeast samples with the same amount of yeast, the same amount of sugar. Different temperatures will have those yeasts rise at different rates. Even the type of yeast. This is something I know personally through my experience with home brewing. We can have totally different yeast values. There are some yeast that prefer cold fermenting temperatures, and they produce yeast, and they produce a lot of the yeast, but at a very slow rate. While you can have some warmer yeast that produce a lot of yeast quickly, but they need to be hot. They don't produce as much, or they don't produce as much CO2, but they produce it a lot quicker. So like some convect yeast, or things like that. So those are other limitations, other expectations going on with this. All right. If you guys have any questions, make sure you ask. If not, thank you guys for watching and good luck with the rest of the labs.